Last time we talked about the basic structure of C# programs deep down and demonstrated a mental model for evaluating C# code yourself by hand. So you get a feel for how the code operates and what the computer will do. Even though under the hood this of course works quite differently from what we do by hand. Nonetheless, it helps you a lot when designing programs. It's something I use after years and years of experience with C#. It's still the way I think about it. So it is quite helpful. Maybe let's start by reviewing what we learned last time. I'm gonna start a code block up here. And I still can't draw curly brackets for the life of me. Well, maybe under circumstances I would be able to draw it, but right now I don't really care that much. I'm gonna start with an int a, which is 10. And then let's do another one. Int b equals a divided by 2. And the way this works, I'm gonna draw a line here. This is the code on the left here, and on the right is where we work. So first we're gonna need a little table. Let's put it like that. Let's make a header. And we're gonna have type, name, and value. And so first we're grabbing, oh, forgot to close it up here. That's better. We grab the first instruction, which is int a equals 10. And we're analyzing this to find all the operations that happen in here. Well, first we have int a declaring a variable, and we have a equals 10 assigning a value to a variable. And because of operator precedence, we first have to define or declare the variable and then do the assignment. So int a means we add an entry in our table for an integer named a, which initially doesn't have a value. So we're left with a equals 10. This is an assignment, which means we write a 10 into the table where a is stored. And if we go down on our table, entry a is here, we write down a 10. And with that, the instruction is done. There are no more operations to perform. And we can move on to the second instruction. Int b equals a divided by 2. As a reminder, the / is division. We have 3 operations now. Again, a declaration and an assignment, but also a division. And the division takes priority over both of them, so that's where we're going to start. That means we have to divide a by 2. So there's a hidden fourth operation in a way, the lookup for a. A is on our table and it has a value of 10. So this is actually int b equals a, which is now 10 divided by 2. And we perform the operation. That means int b equals 5. Next operation, the declaration, just like before. We add a new entry, int named b, with no value, and then we have b equals 5. We assign the value in the table, 5, and we're done with that instruction. Clear out our space here. And with that, our code block is done as well. There are no more instructions. What I didn't mention last time is that essentially these brackets, entering our code block and leaving it, has a special effect that we only really see when we introduce a code block inside a code block. let's just try that in here. I'm gonna move this out a bit. Indent this. And we're gonna open a new code block in here. As I mentioned last time, inside a code block we can add as many instructions or other code blocks as we want. That's perfectly fine. It's perfectly valid code. One instruction, one code block, and this code block contains also one instruction. Also, let's reset the table. But yeah, let's reset the entire table. When we start operating, we're gonna perform the first instruction again, just like before. So let's put those values back in. There was no need to really delete it. It's not gonna do, that is. And once that instruction is done, we're entering the next code block. And because we're entering a new code block, we're actually creating a new table. The old table still persists, it's still there, we're still gonna use it. Just we have now an additional table with a type, a name, and a value column. And now we can perform this operation. Int b equals a divided by 2. We first have to look up a to make the division happen. And to look up a, we check both tables. Or not just both, all the tables we have. And if we find a anywhere, up here for example, we check that value, and now we have, I'm gonna skip a few things in the future, can divide it by 2 and have a 5. Now we have to declare a variable. When we add new variables, when we declare something new for the table, we're only going to add that into the newest table we have, or the lowest one if we write them below one another. So this is where we add b. Again, I'm skipping a few steps now, because I think it's clear how everything operates. This is now the state in our program. We have two tables. One contains A, one contains B. And now when we finish this instruction and leave this code block, when we close the brackets here, that is when we delete the entire table and everything that's in there. Only this one though. That's the table we created when we entered this code block, and that table is now deleted. And then we close the program for good with this bracket on here. However, when we change something in here, let's make this a bit bigger. We could go for a equals b plus 1. We would still operate the first line, like now. And then down here, we would have the table again. I'm just gonna copy the old one. Let's put that in here. So this one is, once we complete the second line, this is gonna be int b5, like before. Now this instruction, a equals b plus 1. Assignment, addition comes first. So we have to look up b, which we look up in both tables. It's not here in this table, so we look in this table. There it is, b is 5, so a equals 6. And now we have an assignment of a equals 6. So we look in both tables and find a in this table and set it in this table as well. It's now 6. Why don't you? That's better. Change it to 6 and instruction is done. We're leaving this code block. That means we delete this entire table again. And our code is done. The difference is now the change we made in this code block still persists. We deleted the second table, but the changes we made in the first table stay. We don't reset those. Those remain. So it's not like this is an entirely new program that is independent from the other. After all, we were able to load data from the upper table. So we're also able to change data while we're in this code block in the old table, and that will remain. It's only things we add while in this code block that get deleted. This has other consequences, and let's talk about one of them. Because it's sometimes useful, even though you're not consciously doing it a lot. If I make another code block now here, it will of course get its own table, just like this one did. But this one has its table and this has its own table. So these two code blocks will get their own table. So I can just make a new declaration for a variable called b. If I were to do variable a, that would not be valid because there is already a variable declared called a. I can't make a second one. The name is unique. You're only allowed to use a name once. But in this scenario, I have two code blocks with their own table where I declare b. So once this code block ends, there is no more variable b. So when I enter the second code block and declare a new b, that's fine. There is no more b declared anywhere. Unfortunately, this scenario here doesn't work anymore, even though in theory it should. After all, we declare variable b in our second table in here. We remove the second table, so when we run into this instruction down here, well, we only have this state up here with only a variable called a. The compiler doesn't see it that way. The compiler doesn't care. Even if you declare the variable down here, it is still considered part of the table for this entire code block, and so it is reserved. You can't reuse it. If you have a name inside a code block, all their sibling code blocks, the parallel ones, can reuse that name, but you can't jump between levels. Again, you're not consciously using that feature a lot, presumably, but it's good to know that it works. Another way to think about this whole thing now is that this code block creates a sort of isolated environment to a degree. It is still connected to our original code up here. We can still change that data. But we can also create new data that is not referenced outside. If I try to access b down here, that wouldn't work anymore. b is created inside this code block in its own table, which is then deleted once we end the code block. So once we reach this line, there is no more variable b. So that doesn't work. In general, it doesn't matter what we do in here, b doesn't exist outside. So whether or not we declare a variable b in here at all, doesn't matter. I can use b only if I declare b up here. I didn't. So down here, no variable b. If that happens in here, that's entirely independent. And any variables I declare in here are also removed later on. only if I actively choose to engage with data from outside this code block will anything actually change. And this is quite a useful behavior. By the way, this nesting of code blocks, having this independent code block with its own table inside our larger code block, that's scoping. The term scope comes up in a couple of places in C#. This is one of them. This variable b has a limited scope. It's only inside these two brackets, or between these two brackets. Only in this code block. The variable a has a larger scope. It exists inside this code block here, but also in this larger code block outside. So if you see someone talking about scope, they might refer to just these code blocks nested in other code blocks. Well, usually they are, though maybe they don't talk about code blocks specifically, but some other constructs that effectively just use code blocks. And we'll see quite a few of them in the future. I mentioned that this code is somewhat independent. It has a level of independence from the rest of the code outside. In the sense that the code outside doesn't really care about the code internally. It's not required. Again, I wouldn't be able to access variable b even if it was declared inside this code block. So why care about the declaration of variables inside at all? That means we could just skip the content in here and our program would work just fine. It's not really doing anything to us. Our program doesn't... Please undo, please undo. There we go. Our program doesn't really get damaged by that not being executed. At the same time, we can execute it and it's not gonna have an adverse effect outside. It's, as I said, somewhat independent. And that's a very useful feature. Because that means we can, using these code blocks, now introduce something we had used quite a lot in our assembly episodes. We're talking about branching, the ability to change the code's behavior during runtime. This code executes this instruction and then ends. Every single time you run this program, it will run these two instructions. Let's say I want to have a program that changes its behavior depending on specific values, on specific input. Let's say I want to have an integer b, and I want that to be equivalent to the absolute value of a. So if a is a 10, I want b to be 10. If a is minus 10, I want b also to be 10. How can we achieve that? The most straightforward method would be to run code in case a is negative, to convert it into a positive number. And to just use a as is when a is already positive. So int, actually let's just declare it for now. Can just assign it to a directly if it's positive, but we would like to make it minus a. Actually, let's write that out into individual squares minus a if it's negative. Minus a just means minus 1 times a. It's just the inversion of whatever a is. If it's a plus 10, it will now be minus 10. If it's a minus 10, it will now be plus 10. You can just put the symbol in front. That's fine. In our assembly, these alternative code branches, this decision of running or not running certain code, was done doing using conditional jumps. We had 2 jump operations in our assembly language that would react to the accumulator being 0 or the accumulator flag being set, and based on that would either do the jump or just do nothing. And that would let us change the way the program behaved, because it would either continue running a certain code that follows the jump, or it would go to another part in our memory and execute that code, which could have completely different behavior, or should at least. Otherwise, why bother with a conditional jump? And in the extended syntax, we expanded this a bit to a block of code that would get skipped if a condition was met. Skip if flag is set, or skip if variable, or skip if the accumulator is 0. And the same structure exists in most normal programming languages. Okay, normal is unfair to say. In most procedural programming languages. Actually, all of them, I think. I'm not aware of anything that has alternative code branching rules. The basic structure looks like this. We start with a keyword, if. And then we follow that up with normal brackets. Not curly brackets, not square brackets, just the regular good old round normal brackets. And in these brackets, we define the condition. C# is a more advanced language than what we worked with so far. So of course the conditions can be more advanced than only if accumulator is 0. We can actually freely define a condition that can be as complex or simple as we want. And this condition determines if a code block that follows directly after gets executed or not. If this condition says yes, please execute, then whatever we put in here, in our case that would be the b equals minus a, would get executed. If the condition says no, it doesn't apply right now, then the code block that follows, so this one here, is completely ignored, and we continue with code after here, which is just gonna end the program. And to understand this, let's remove that. To understand this condition, we need to introduce a new data type. So far, we've talked about integer data types. Last time I introduced you to byte, short, int, and long. Just different variations of integers. The only difference being that they can store larger and larger numbers. For conditions, there's another data type that's relevant that is not a number. It is called bool, short for Boolean. Actually, let me write that out a bit clearer. Something like that. Booleans are only 1 bit. They can only be 1 or 0. Yes or no. True or false. That's all. They only have 2 possible states. And in C#, we care specifically about these two terms, true and false. Because that's how you write a bool. Just as you write 1, 2, 3 for integer or byte or whatever, you can write out true, the actual word true or false as a word, and the computer will accept that as the value for a boolean. It won't accept a 1 or 0, it won't accept yes or no, it will accept the words true and false, the actual words. So we could have a boolean b equals true. This is a valid instruction. Booleans are used whenever you have a decision to make, whenever something boils down to one or the other, and that of course includes conditions. In these brackets, what the computer expects is a value that is equivalent to a boolean. Or specifically, it expects a boolean value in here. So either we write down a true, in which case we will execute the code in here, or we expect a false, in which case we will ignore this code block. And since the point right now is to make a decision at runtime, we can't just write true or false on here. That would be the same as just writing the code or not writing the code before we actually compile the program and ship it out. We have to generate a value based on the condition of A. So how do we generate Boolean values? With special operators, of course. So we had operators like plus, which use two values, one on its left, one on its right, performs an addition, and it generates a new number, a third integer. It takes two integer numbers, generates a new integer number. For example, this is 15. There are other operations possible with two values that don't generate an integer, that don't generate a number. One of them would be this symbol, the greater symbol. Greater than. Instead of an operation that calculates the sum of these two numbers, this is now turned into a statement. 10 is greater than 5. This statement is true. So what's happening here is when the computer operates on this operation, if it performs this operation, it will either generate a true or it will output a false, depending on whether or not that statement is true. 10 greater than 5, true. 10 greater than 15, false. Quite easy. And of course there's a counterpart. We could switch, for example, the sides, but we could also switch the direction of that arrow. And this is now 10 less than 15, which is true. And 10 less than 5 would be false. It is just another operation that just doesn't generate another integer, it generates a boolean, a true or a false. In our case, we wanted to test if A is negative. And another way to say that a value is negative is to say it is less than 0. So if A less than 0. Let's try to operate on this. Let's try to perform this or run this program by hand. The first line, int a equals 10. I'm gonna skip the specifics right now. Int a equals 10 because this is pretty standard. Int b equals a, so make an int b, set it to 10 because that's what a is right now. And now we reach this line with the if. the if itself is no operation, it's a decision, it's a structure that tells the compiler that it needs to make a decision on which code to operate on next. Basically, internally it jumps to a different part of the code, the conditional jump. And to determine where the jump goes to, we have to first evaluate this code in here. That is our actual instruction we have to perform now for this if. So a less than 0. Well, only one operation, the less than. We look up a, which is 10. So we end up with 10 less than 0. And this operation results in a false. Was about to write true there. And so this construct decides to not execute this code block, because we end up with a false in here. Of course, the code isn't changed. The undo is not working the way it should, and I'm frustrated why it's not working. The mother fingers. Some of the gesture for undo is not reacting as quickly as it should. I'm not sure why. Maybe the fingers are spread too far apart? Yeah. So our code is skipped and we just end the program. And B remains at 10, which is correct. Now if we change this whole thing, and this is actually a minus 10, then when we reach this if, we have to evaluate this expression inside this instruction, a less than 0, which in that case would be minus 10 less than 0, which is true. And so we have in here, if true. That means this time we jump into the code block in here and start executing this code. Of course, again, with its own variable table. We start a code block, we create a new table, and we set b, the existing variable on our upper table, to minus a, which is plus 10. And the code exits. Our secondary table, which remains empty, will be deleted, and our program ends. But this time the end result is plus 10, so just 10. We changed how our code behaves based on this condition. Simple, right? I mean, I've been talking quite a bit about this now. For very, very simple concept, actually. Let's change things up a bit. What if my condition is a bit more complicated? What if I'm not checking if a is negative? What if I'm checking if a is in a specific range of numbers? What if b starts as a 0 and I want b to be set to a, to the same value as a, if and only if it is between 1 and 10 inclusive. So if the value is less than 1 or greater than 10, I want it to remain at 0. But if it's in that range, I want it to be set to a. How do we do that? Well, first of all, let's add these two variations. To determine just if something is greater than 1 or 1, the inclusive part, we have another operation. So 1 greater than 1 would be false, because 1 is not greater than 1. But we can use another operation by including another sign in here, another symbol, the equals sign. Now it's 1 greater than or equal to 1, which means we check if this value on the left is at least this value on the right. It can be the same, it can be greater, It just cannot be less than. And of course the counterpart, less than 1 or equal. So these check if the value is greater or is less than another, and these check if it's less than or greater, but also with the possibility that it can be the same, and that's valid. And so we want a to be greater than or equal to 1, but we also want a to be less than or equal to 10 in our code example. So we have two different conditions right now. There's a way we can achieve that directly, because I mentioned that a few times now, last time and this time. Code blocks can be stacked. You can have code blocks and code blocks and code blocks, no problem. And this if up here, that's just attached to that code block. Nothing more, nothing less. It's still just a code block that might or might not be executed. So of course we can just start with an if up here that first checks if a is greater than or equal to 10, and then we open the code block, and in this code block we make another if that checks if, oh wait, not greater than or equal to, less than or equal to, and this one is a greater than or equal to 1. That's better. Which gets us another code block, and now we can set b to a. And we close this one, and we close this. Let's just write this out now. And we close this one. So we are now 3 notations in. We have the outer code block, then we have this first code block, and this second code block internally. If a is in the range, so right now it's 10, then this condition will evaluate to true. 10 is less than or equal to 10. It's equal to 10, so this condition evaluates to true. So we enter this code block, and that means we hit this second code block with an if, and we check if a is greater than or equal to 1. 10 is indeed greater than 1, so it is greater than or equal to 1. So we enter this code block as well and execute this code. And we set b to a. And then we close the code block here, and then this one here, and then our program is done. And of course, both of these code blocks create their own table. So technically when we're down here, we have another table for this code block, and then another table for this code block, which then gets deleted first, and then the upper one. It's just we don't do anything with those code blocks yet in terms of creating new variables, so I didn't bother creating new tables. This is now giving us the option to execute code if that value, if a is within the range. If it was greater than 10, then this would be false and this entire code block would be ignored. Nothing would happen. If it's less than 1, well then this would be true and we enter this code block, but then this one would be false and we skip this part and enter the outer code block. So we are guaranteed to execute this code only if we're in the range. Let's switch that around. What if we want to set b to a only if a is not in this range? If a is either greater than 10 or less than 1. Alright, so here's a little trick that you will use quite a lot without realizing it. Since we have a very simple condition for it's either this value or this other value, we can just switch the assignment and we start off with be being equal to a, and then if it's within the range, we set it to the 0. So we didn't need to change the structure of the program. We just switched the values we assign by default and the value we assign with those conditions, and that way we get the correct result. If A is within the range of 1 to 10, then B will be 0. If it's outside of that range, if it's less than 1 or more than 10, we will set it to 0. Or will we? No, we won't. That was totally a test, I didn't misspoke accidentally. If it's more than 10 or less than 1, we will keep B at A as intended. If it's within that range, these two ifs will both be true and we assign 0. So there we have it. That's how we switch the condition there. There's a different way we can approach this though. Let's say I want to keep this logic in here. I want to initialize it with 0 for some reason. I want it to start at 0 and then switch to the value of A when it turns out we need to. No? We can switch the condition. Let's actually return this quickly. What is the opposite of A is less than or equal to 10? A is greater than 10. Simple, right? It can only be less than, equal to, or greater than. And if it's not less than or equal to, it can only be greater. So this is the opposite. And that means A is outside of that range. And in that case, we set B to A. What if A is less than 1? We don't capture that here. So we make a second if. Oh, I forgot the brackets. Make a second if. And this one checks if A is less than 1. And then we set B to A. So now we have two separate ifs next to each other. Each checks its own condition, and both result in the same code being executed. And what I did here up there, out of habit, is a special rule you can apply for things like this if, which follow a very specific pattern of if, brackets, condition, close bracket, followed by a code block. If that code block that follows this has exactly one instruction, only in that scenario it has to be, doesn't allow any empty stuff, it has the code block that follows has to consist of exactly one normal instruction. In that specific case, you're allowed to ignore the brackets. It's like the compiler pretends there are brackets here, even though we don't write them. Makes everything a bit smaller. So that's what you usually do. If it's just one instruction, you write that out like this. You still indent it as if there was a bracket, but you don't write the brackets out. Only applies to single instructions. If you do nothing, so if the code block is empty, or if there's more than one instruction, so at least two instructions or one instruction and another code block, or if it's just another code block inside the code block, anything other than one instruction, you still have to write the brackets out normally. But yeah, so this is now code that will assign a value to B only if A is not within the target range. Let's imagine this code is a bit more complex. Let's say it's not just one instruction. Or maybe this operation is a bit more complex here. The whole instruction itself with way more operations. We wrote this down twice. And if there are several instructions, we would have to write them out twice. Exactly the same code, just written twice. Not great. Well, there's one workaround. We can create a new variable. Let's say we call it C. I'm going to start at 0. And the code in here is just going to set it to 1. And then we can have another if down here. If C is greater than 0, then we assign B. So we have these two conditions that both change this one value that is then evaluated once. So our actual code that we want to use these conditions for is only written once. And of course, instead of an integer, we would use a bool. Which could start out as true, or, like in our case, probably better, false. Then we set C to true. In either of these cases. And then down here, we don't have to make an operation. We can just use C directly. This doesn't have any operations, so when the computer tries to evaluate the content of this bracket, it's just the lonely C, which is at that point either false or true, which is all we need for our if. So this is a way we can combine different conditions. It is, however, still a bit much to write. Every part of our condition is now suddenly its own if, and we have to set a variable here to true or false or whatever we do in that case. And let's say this is not the only condition we apply this to. What if we make this a bit more complex by adding a second range we want to avoid, or a third one? So more variables we have to look out for. Creating new ifs for every single possible condition, just so we can combine everything, is a lot of work. A bit ridiculous. C# is more complex than that. We can combine these conditions without writing them out as individual ifs. Before we can talk about that, let's finish up quickly our comparisons, because there's one still missing. We have the less than, we have greater than, we have less than or equal, and greater than or equal. You might see a pattern here. There's still one thing missing. There's one specific thing we can't test with these four on their own. And that is if it's exactly equal. If I want to test if 1 is equal to 1, or if I want to see if 1 is exactly 1, not less than, not greater than, exactly 1. And I want to do that in one operation. I could of course test if it's greater or equal to 1 and if it's less than or equal to 1. If both are true, it must be 1, but I don't want to use two operations for that. I don't want to combine two different conditions. The symbol for that is one you already know, which makes sense. It's the equal sign. Only the equal sign already has a meaning in C#. We use it to assign variables, which is a valid operation on its own. And there are a lot of situations where you can actually legitimately write out an assignment and a condition for comparison at the same time, where both would be valid code pieces. So the compiler cannot decide for you which one it is in all cases. In many cases, the compiler would be able to determine, yeah, you meant the comparison, not the assignment, or vice versa. Not in all cases, though. And therefore, we don't use the equal sign for comparison by itself. We need another symbol attached to it. Another equal sign. That's something that you will have to get used to. If you want to check if a value is exactly another value, we have to write it as equals equals. It's a bit weird. C# isn't the only language this happens in, and as in many other languages, because the single equals is valid in many cases where the equals equals would also be valid, there are some famous programming errors, just very quick oversights by a developer that cause serious issues. Get used to that. If you mean equals, you mean equals equals. Just maybe as a rule of thumb, assume that for comparison you need two symbols for the operation. Exception is the less than and greater than, but everything else, two symbols. Maybe that will help. But these are all operations that take two values, like two numbers, and generate a Boolean. So they take an int and an int, int, and another int, and they all generate a bool. Just like plus, minus, times, division. They all take an int and generate another int. These are comparisons. They take two ints, get a bool. These are math operations. They take two ints and generate an int. There's another set of operations that generates a bool, but that take in bools. Can take a bool and another bool, and it generates a bool. These are Boolean operators, fittingly named, and there are a few of them, but the most important ones that you absolutely have to learn are AND, OR, and NOT. And actually, with new C# you could actually write out AND or NOT as words, though that doesn't work in all situations that you might want to use these operations. And using them has certain connotations, some side effects that we will talk about at some point, especially once we get into pattern matching. But this is just what we can call them. There are symbols for these operations. But let's talk about what they do first. And I assume most of you already have an understanding for this, but these are operations that take two booleans, in this case, or one boolean, in this case, and create a new boolean, which you can express using a very simple truth table. Again, there are more than these operations, so essentially for every combination in a truth table, there's an operation. And a truth table is simply, we have two input numbers, like A and B, and we have an output. And let me write that B correctly, because this is annoying me right now. Better. So let's say we have two inputs, one is false and the other is false. Keep in mind, we operate on booleans now, so input is only going to be true or false. We have false and true, we have true and false, and we have true and true. And the output for the AND would be false, 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 and true. For the OR, it would be, let's maybe write this out as, yeah, I told you to delete. And and we have the OR. That would be false, true, true, true. And the NOT doesn't operate on two values. We just have one input, false or true, and it would just take true or false. The AND is true if both inputs are true, not in any other case. Only if A and B are true, if A is true and B is true, the AND is true. The statement is true. If A or B is true, then the OR is also as a whole true. So if both of them are false, the OR is false, but if at least one of them is true, then the OR is true. And the NOT is just whatever A is not. It's inverting the value. These are truth tables. And I can try to write this out a bit more nicely, but I'm failing. Oh well. These are the most common operations, and the cool thing about this trio of operations is that you can use any two of them to emulate the behavior of the third. You can recreate the AND by just using ORs and NOTs. You can recreate the OR by ANDs and NOTs, and you can recreate a NOT by ANDs and ORs. So any two of these three can emulate the third one. It's quite cool. It's about it can be a bit confusing to work with those values then, so always know all three. That's best. Just saying. And now how to use them. Well, things get a bit interesting here. Bit being the keyword. There are variations of these operations in C# that technically all work, and at least if you're using Booleans, they do generate the same output. What do I mean by that? Well, for AND, we have this as the operator, the ampersand, but we also have the option of ampersand and ampersand. So you can write it as a single symbol or as a double. And these have two different meanings, though they both will perform the logical AND. They will both behave as this truth table predicts, but in different ways. And for the OR, it looks pretty much the same. We have the pipe symbol, just the vertical line, or we have the OR like this, with two lines. And then we have the NOT, which actually does have two different symbols. So the logical one, the one you will most likely use most of the time, is just an exclamation mark, weirdly enough. Honestly, I always felt that is a weird choice, but oh, whatever. And the equivalent on this side would be the tilde symbol. Or I believe you call it tilde, this squiggly line. The difference here is that the ones on the right only operate on Booleans. Only Booleans. The ones on the left apply to Booleans, well, except maybe this one. Let's put it like this. These 5 operate on Booleans, but these 3 bool can work also on... Oh wait, no, not Boolean. These 2, he can work on integer numbers. Boop, boop, boop. I'm just going to give you a quick example of what the integer numbers would do. Let's say we just take a byte. If a byte b equals, what do we use? 5. Let's make a small, simple number. And you can set byte O to tilde b. What this is doing is it will invert the bits in b. So this would be, for example, 5. So we have 0, 0, 0, 0, 0, 1, 0, 1. It's a byte, so we have 8-bit. And the 5 is these two digits being 1. And this operation will now apply the NOT operator. So it will invert the bits, all of them, individually. So that is the result. Now here's a pop quiz. What is this number? What kind of data type is byte? Is it signed or is it unsigned? I said byte, I didn't say ubyte. Trick question, of course. Well, not really a trick question, since that wasn't the question itself. But the alternative would, of course, be the S byte with the signed byte. The byte itself would be unsigned. So this number is effectively the highest number you can have in a byte, which is 255, except these two ones on set, which would add up to 5, so this is 250. So we go from 5 to 250. And if you used byte A now, we could say it's B and O. And when this is evaluated, we would make an AND between all the individual bits, between this two and these two and these two and these two. And that would get output in A, which, of course, because B is inverted of 5, means every single bit is guaranteed to be 0. If the one in B was a 1, the one in O will be 0. It has to be. That's what the inversion does. The NOT operation on every bit. We could also go for byte. Okay, now I regret my choice with the naming. Let's be confusing and call this one I, which will be B or O. This will apply the OR operation between these two, all of them individually. So this will be a 1, and this will be a 1, and every single one will be a 1, guaranteed, because one is just the inverted version of the other. So if the old one was a 1, the new one will be a 0, but there's still a 1. If the old one was a 0, the new one will have a 1. So there's guaranteed to be a 1 in at least one of those two bits every single time. So that's the outcome there. But this is when you use integer numbers. There are some other operators, logical operators you could use. Let's use the last one, because this one comes up a lot as well. Let's call it X, which is gonna be B. And then we have this little hat symbol. This is an XOR. That's a different logical operation. I haven't discussed that before. The XOR is true if exactly one of the two values is true. So that 2 would also be just once in this case. But basically it's true if we have 1 and 1 0. If both were 1 or both are 0, the individual bit would be set to 0 in here as well. That's for the special ones when we apply them to numbers. We're talking about just purely Booleans right now. And that allows us to do this. Start with an I for if, open the bracket. And we're trying to use our first program now. If A is within the range of 1 to 10, we're gonna set B to A. If A is greater than or equal to 1, that was the first condition. And let's not write that as an F. And A is less than or equal to 10. Then we're going to set B to A. This is technically doing the operation, but you have to be careful now because of operator precedence. And honestly, I'm not really sure about this one right now. Thing is, this and this ampersand can work on numbers as well. So the system might decide that what you're doing here is 1 and A, instead of the Boolean from here and the Boolean from here combined using an AND. I'm honestly not sure. I think the precedence was actually that the AND would be evaluated first right now. I'm not too sure. So technically I would have to add brackets in here to make sure it's not. But I'm not too sure about that right now. That's where having an IDE or just a compiler would be useful right now. Or the table with the precedence. But thing is, you rarely write code like this. It has its uses, but as long as you're working with Boolean operations, it's unlikely that you will encounter these single symbol variations. What's more likely is that you're going to use the double AND. It is still behaving the same. We have Boolean on the left, Boolean on the right. This one only works on Booleans, so you don't have to worry about the operator precedence anymore. It cannot apply to the integers. So the computer knows first we evaluate both sides, and then combine that in one AND. So actually that's a lie too. We should probably talk about that now. So when we get to this point in the code, table is finished, we have 10 and 0 and A and B, and we evaluate the condition, which is A greater or equal to 1 and A is less than or equal to 10. Well, we have this as an operation, we have this operation and this operation. This is the last one we do. These two have precedence. They themselves are equal, so we're going to start with the one on the left. And what we're going to do here is A is greater or equal to 1. Yes, it is. So this is a true. And A less than or equal to 10. And here comes a little weird thing. The computer looks at this value now. It sees we have an AND with a true on its left side. It's not just looking at the operations right now. It notices this is a logical AND combination. So it actually does some thinking before it continues with its normal flow. It sees a true on its left side and decides, yes, this has a chance to result in a true after all. So now it will continue with checking the rest and performing now this operation, which will be also true. And now it evaluates to true. So this results in true and B equals A. Let's try the inversion again. Let's try the other thing we tried. We want to set b to a only if a is not in that range. And one option would have been, actually let me write this back in, greater than or equal to 1, less than or equal to 10. We could just add a not in front, put the brackets behind, and then this result would simply be inverted. Whatever we add in here, if it's true, then we generate a false from that. If it's false, we generate a true from that. So we could just invert it with a simple not in front and some brackets. It's not doing the undo. No, I'm gonna just, let's do it with this. Can't be bothered. Now the way we do it now is if a is less than 1, or with a double O, a is greater than 10 with a double, not O, double OR. Now we get to this code, evaluate the condition less than 1 or a is greater than 10. We still start with the operation on the left. This one is last. These two have precedence over this OR in the middle. The one on the left has precedence over the one on the right. So a less than 1, a is 10. This is false. All right. Or a greater than 10. We elevate this, evaluate, there we go, that. And we end up with false, or it's not greater, it's also false. So the entire result is also false. And so we don't execute the code. Right, so similar behavior to the end. This all changes if, for example, we add a 0 in here. If we evaluate now a less than 1 or a greater than 10, we end up with a true or a greater than 10. Well, see, the operation is an OR, but the one with the two pipe symbols. And this time, the computer checks first the value on the left and the right, and it knows on the left I already have a true. And this is an OR. The OR will be true if either side is true. It is already set in stone that on the left side there is a true. We already know that. So the computer knows that this result of this OR, no matter what happens on the right side, will be true. And so it will simply skip to just evaluating to true directly, and despite the precedent saying this operation should come first, it will ignore the entire part here. Just gone. We evaluate to true and we execute this code. We're taking a shortcut. We don't need to evaluate this condition on the right. We don't need to process that. We can directly execute this code. And if we go back to the AND from before, the same happens, just in the opposite direction. So a greater or equal to 1 and a less than or equal to 10. Well, once we reach a greater 1 and a less than or equal to 10, well, is a greater or equal to 1? No. So this is a false. And a less than or equal to 10. And again, it sees it's a double operation. It has two operators, but it notices this one is the AND with two ampersands. which has the special meaning of check the value on the left, check the value on the right. It knows the value on the left is already false. So no matter what happens on the right, the output of this AND is already determined to be false. It cannot be true anymore. It doesn't matter what happens. So it also skips the part on the right and directly goes to false. It doesn't even bother operating this. No need to process any further. So in this case, we also just skip the if in total. We just end with a false. And don't bother determining the rest. Which can be quite useful if the stuff on the right gets lengthy, if there are more conditions associated with it. If there's a long chain of conditions, maybe with a lot of calculating internally. I mean, after all, we can also, instead of just less than or equal to 10, b plus 10, for example. There's no reason we can't add an addition in here, which would have precedence over the comparison. So to evaluate this part here, we'd have to first perform an addition and then make a comparison. But this AND here directly cut us off and said no possible way to achieve this anymore. Why bother wasting resources on calculating this if it doesn't affect the AND behavior? You can skip. The normal AND would not do that. Assuming that you only compare the booleans, it will calculate both sides first and then perform an AND operation on the boolean and then decide whether or not to execute the if block. So the double version will cut the processing short. It will end evaluating the condition once it knows for sure that a certain end result will be achieved. The single symbol versions will execute everything as you would expect and then make a decision. So that's the difference. These will cut short first, these will evaluate completely, but these also operate on a different baseline because they're not logical comparisons in that way. So it's simply compare booleans. They generate new values by combining all the bits in the input values, which for integer numbers generates completely new numbers, but for booleans, which are only 1 or 0, it's effectively the same as a logical AND and logical OR, because there's only one bit you're interested in. And this is not just a convenience feature, this has implications down the line. I'm hoping we can get there in maybe 2 or 3 episodes. Do you see how this will actually change the behavior of the program then? Where the decision whether or not to use 1 or 2 will change how the program behaves. This has important implications that this shortcut happens, that it just cuts out the code on the right here. So keep that in mind. Usually you will use the double versions. If we're making just conditions, if you just compare booleans, you will usually end up with 2 ANDs, 2 ORs. So 2 ampersands or 2 pipe symbols. That's the default use. That works quite fine, and you won't run into issues where they accidentally have the wrong code executing. It's just useful to keep in mind that there is a difference. And since we have 10 more minutes, let me show you one more thing. It's about booleans. Let's clear this stuff out. It's just some Boolean logic, how you can apply it. So this is a bit more math actually. Just with Boolean values. Boolean algebra. So let's say we have 2 values, A and B, and they can be true or false. Well, the way you write this out a bit more mathematical, there are different standards for writing this out. The one I personally always use, I would have either for an AND, I would write out A and B, or just AB. Because an AND is like a multiplication. That's the way you can imagine it. One of them is 0, then the end result will be 0. So if one of them is false, the end result will be false. The OR is the equivalent like an addition, though the logic falls a bit apart there. But it's still, if you add the two numbers, is the end result greater than 0? And that would be either OR B. But you could also write this as A plus B. So in the same way you can A times B, you shorten this to AB. You can also write A plus B. And the NOT, well, we could have A with an upper score, or we have the NOT in front, that symbol. Those are the different variations I know. And I usually end up mixing that when I make my own notes. So I could have A, B, or not A, B. And the cool thing is, if you imagine the NOT a bit like maybe a minus, but more importantly, the OR behaves like addition, the AND behaves like multiplication. Well, this is a bit like A times B plus minus A times B, sort of. There are certain rules you can apply. So, for example, A and not A or B. Well, you can combine this to A and not A, or A and B. It's like multiplication. Multiply this with this, and then multiply this with this. So in other ways, what you could also write, what I would usually write is A or B. That's the same as AA or AB. Right, and you can also convert this in the other direction. And then you have things like AA, A or A and not A can never be true, because both need to be true, and we by definition have at least one of them false. So this is always false. This is false or A and B. And false or something is the same as just AB. So you can use some Boolean algebra to simplify a lot of conditions. I mean, this is, of course, a manufactured example, but you will at some point run into cases where you have 3-4 different combinations of input values, sometimes combinations of these values with each other that affect one another, and things get complicated. But with Boolean algebra, which you probably should look up yourself, you can do a lot of simplification yourself. In the extreme case, you can always just end up making your own truth table with all inputs and all outputs, and then maybe based on those outputs you will see a pattern. That's also a possibility. One thing I always end up using in a lot of cases, so A or not A and B, for example. So either A needs to be true, or A needs to be false and B needs to be true. Let's say I want to invert this entire thing. I want the opposite result. So eventually I want to make this inverted, not all of that. The way that works is you invert any single component in here. So you invert the A to not A, and you invert this to, well, A was inverted before, now it's not inverted anymore, but B is now inverted. If you invert twice, you just return to normal. Not is true. True is, well, in this case false. Why is it not resetting? The undo function makes me mad. So we invert every single component in here. And we we switch the ands and ors. So right now this is an or, so now it's an and this was just an and, so now it's an or. So in other words, this is not A or B. Not A or B. And since we already established, this will always be false, so it's only B. So the inverted result of this is B. Unless I made a mistake here. Actually, I might have made a mistake. Wait, this... Let's make a truth table to verify. Let's say this was just for practice, of course. So, false, 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 true, true, false, true, true. All the possible inputs for A and B. And this first one, if A or... So, this one is definitely true because... No. These two down here are true because A is true. This is not A and B is true. So, not A, not B, that's false. This is not A and B, this is true. Alright, that's the end result. Oh wait, inverted B. Sorry, forgot that. But definitely not true. What if... Yeah, I made a mistake here. This looks more like not A or B. I'm feeling really stupid right now, but that's probably a good thing. Oh, wait, right. Forgot the brackets. So, wait, that should at least make more sense. So we have not A and not the A. Undo. There we go. And A or not B for the brackets. So this is actually... Yeah, this is not A and A, or not A and not B. This is false, always. We can then skip the or, and that means we have just not A and B. And not A and B is just A and B, but in reverse. So not A and B, this... Well, no, not A and B. Wrong. Not A and not B. So these two are true in that case? I still have a mistake here. You know what? I'm not gonna think about it further. I'm just being stupid and maybe you should ignore me. Holy. You know, I was pretty convinced I knew my Boolean algebra. I didn't. Look, in programming that largely still applies, so if a less than 0 or b greater than 10, if you want to invert this whole thing, just have a greater than 0 and b or greater or equal to 0 and b less than or equal to 10. So these two are functionally equivalent. So you invert every single statement in here and you invert the ands and ors, and that gets you the inverted result. So instead of making additional operations, you can just convert everything by yourself, by hand, and you have one operation less to process. Makes your program a bit faster. But yeah. It bothers me that I got my code wrong, that I can't get the conversion right in the mathematical way. You know what, I'm gonna look that up myself after the stream, since we're done anyway. Boolean algebra, very fun topic. You can do a lot of cool stuff by just applying that to your real-life programs. So, like optimizing your code in certain places, or just reducing seemingly complex statements to something really simple. Not that you're gonna have to work with that issue for a while. That's hopefully gonna take you a bit before you hit that point in your career, that you need that complex of a condition. Anyway, have fun with branching. The gestures still don't take. There we go. Branching, cool feature. With an if, you can decide if certain code gets executed. You have effectively our skip blocks from the extended syntax here. And with that, I'm gonna leave you. Have a nice Sunday. Till next time.